The real difference between the F-35's F-135 and the SU-57's AL-41F1 is not performance or technology, but the failure each engine was designed to prevent. The F-135 was created under the assumption that the aircraft would operate deep inside hostile airspace, saturated with sensors, passive detection networks, and long-range missiles. In that environment, failure does not come from being outturned or outclimbed. Failure comes from being detected. As a result, the F-135 prioritizes predictable power delivery, thermal discipline, fuel efficiency, and long-duration stability, even if that means sacrificing classic fighter traits like sustained supersonic flight or extreme post-stall agility. The AL-41F1 was designed under a very different assumption. Russian doctrine has historically emphasized kinematic performance as a decisive advantage. Speed, climb rate, and maneuverability were viewed as ways to overcome technological disadvantages or numerical inferiority. In this framework, failure means being out-accelerated, unable to control the aircraft at extreme angles of attack, or losing the ability to maneuver aggressively when it matters most. The engine, therefore, prioritizes thrust-to-weight ratio, rapid throttle response, and compatibility with thrust vectoring, even if that means higher thermal stress, higher fuel consumption, and greater infrared visibility. This philosophical split explains nearly every technical divergence between the two engines. The F-135 was designed to endure inside a hostile battle space for long periods without changing behavior. The AL-41F1 was designed to dominate momentarily through performance, even if that dominance cannot be sustained indefinitely. So, which engine is designed to stay effective longer once the aircraft is detected? A. The AL-41F1. B. The F-135. Drop your thoughts in the comments and we'll look at this later in the video. The F-135 is physically enormous for a single-engine fighter, and that size is not accidental. Thrust can be produced either by accelerating a small amount of air to extremely high speeds or by accelerating a much larger amount of air more gently. The F-135 does the latter. Its large fan allows it to move massive volumes of air, generating thrust through momentum rather than extreme exhaust temperature. This approach is intended to reduce thermal stress on components, lowers infrared emissions, and improves fuel efficiency across a wide range of operating conditions. At full afterburner, the F-135 produces approximately 43,000 pounds of thrust, making it the most powerful operational fighter engine ever fielded. Even without an afterburner, its dry thrust of roughly 28,000 pounds allows the F-35 to climb and cruise efficiently without relying on fuel-intensive high-temperature operation. This is critical for a stealth aircraft because afterburner use dramatically increases infrared signature and fuel consumption. The AL-41F1 takes a more traditional approach. With a smaller fan and lower bypass ratio, it relies more heavily on higher exhaust temperatures to generate thrust. It produces roughly 32,000 pounds of thrust with afterburner and around 19,000 pounds dry. This design provides excellent throttle response and strong high-altitude performance, but it pushes thermal margins much harder. The future Izdalia 30 engine aims to improve efficiency and increase thrust closer to Western standards, but it still follows a Russian design lineage that prioritizes thrust-to-weight ratio over airflow-based efficiency. The difference between these approaches matters deeply. Engines that rely on airflow rather than temperature are quieter in the infrared spectrum, more durable over time, and easier to integrate into complex thermal management systems. Supercruise is often treated as a symbol of fifth-generation superiority, and the SU-57 does possess limited supercruise capability under favorable conditions. With a clean configuration, high altitude, and reduced payload, it can maintain supersonic flight without afterburner. The F-35 cannot. This difference is frequently portrayed as a shortcoming, but in reality it reflects a deliberate design choice. Sustained supersonic flight creates cascading penalties that directly undermine stealth. Fuel consumption increases dramatically. Exhaust temperatures rise, making the aircraft easier to detect with infrared sensors. Structural heating becomes severe, reducing component lifespan and increasing maintenance demands. For an aircraft designed around remaining undetected, living at supersonic speeds is counterproductive. The F-135 was therefore optimized for subsonic efficiency, where fuel burn is lowest and thermal output is manageable. This allows the F-35 to remain inside contested airspace longer, continuously operating sensors and electronic systems without advertising its presence. The SU-57 accepts the heat and fuel penalties of speed because Russian doctrine still views velocity as a tactical advantage. The F-35 assumes that information dominance and persistence matter more than arriving quickly. One engine believes initiative comes from speed. The other believes initiative comes from remaining unseen. Thermal management is one of the most important challenges facing modern fighter engines. And this is where the F-135 truly separates itself from previous designs. The engine is not an isolated propulsion system. It is part of an integrated thermal architecture that actively manages heat generated by the aircraft's avionics, sensors, and electronic warfare systems. Heat is absorbed by the fuel, routed through the engine, and expelled in a controlled manner that minimizes infrared spikes. Without this system, the F-35 would overheat rapidly. The aircraft generates more internal heat than any fighter before it, and only an engine designed from the ground up to act as a thermal sink can support that load. The AL-41F1 does not perform this role to the same degree. Heat management relies more heavily on airflow, material tolerance, and operational limits, which work well for short, intense engagements, but constrain sustained high-power operation when both propulsion and electronics demand thermal capacity. This difference has direct operational consequences. An aircraft that must alter its behavior to manage heat becomes predictable. Predictability creates vulnerability. The F-135 allows the F-35 to operate at high electronic intensity without changing its flight profile, a massive advantage in modern combat. Engines dominate infrared detectability, and this is where design philosophy becomes visible to enemy sensors. The F-135 reduces infrared signature through lower exhaust temperatures, exhaust flow mixing, and partial masking by the airframe. Because thrust is generated through airflow rather than extreme heat, the engine naturally produces a smaller infrared footprint. The SU-57's engines are more exposed, and the use of three-dimensional thrust vectoring complicates signature reduction. Thrust vectoring provides exceptional low-speed control and post-stall maneuverability, but it disrupts exhaust flow and increases thermal visibility. This is a deliberate trade-off. Russian designers accepted a higher infrared signature to gain agility, while American designers rejected thrust vectoring to preserve stealth and reduce mechanical complexity. In an environment filled with passive sensors that do not emit signals, being invisible matters more than being agile. The F-35's engine is designed to hide power. The SU-57's engine is designed to express it. Fuel efficiency determines how wars are actually sustained. The F-135 allows the F-35 to loiter, strike, and withdraw with minimal afterburner use, reducing tanker dependency and increasing operational flexibility across long campaigns. This efficiency is not accidental. It is the result of an engine designed for endurance rather than peak performance. Russian engines traditionally burn more fuel under similar conditions, particularly during aggressive maneuvering and high-speed flight. This reflects prioritization rather than incompetence. Reliability follows the same pattern. The F-135 was designed for decades of continuous use, with advanced diagnostics, predictive maintenance, and long overhaul cycles. It has accumulated hundreds of thousands of operational flight hours, and its limitations are well understood. The AL-41F1 is robust but accepts a shorter service life, particularly when thrust vectoring is used aggressively. The future Asdalia 30 aims to improve durability and efficiency, but operational trust is earned only through time and sustained use. Wars are not won by peak performance in isolated encounters. They are won by engines that survive years of continuous operation. The SU-57's engines chase dominance through power, agility, and speed, even if that means being seen. The F-35's engine hides power behind efficiency, thermal discipline, and silence, even if that means sacrificing raw maneuverability. Earlier, we asked which engine is designed to stay effective longer once detection occurs. The answer is the F-135. Not because it is more powerful, but because it was built to behave the same deep inside hostile airspace, long after performance-focused designs are forced to adapt. One engine is built to win the fight. The other is built to ensure the fight never happens. In modern air warfare, the most dangerous engine is not the fastest or the loudest. It is the one that stays invisible long after others have been detected. If you enjoyed this deep engine breakdown, like the video, subscribe to the channel and let us know in the comments. Which engine matchup do you want next? The Raptor's F-119 engine was built with a simple question in mind. How do you create power that stays invisible? The United States needed a propulsion system that could push a fighter to supercruise and keep noise and heat buried inside the jet. Everything about the F-119 flows from this quiet precision. Nothing is allowed to compromise stealth. The SU-57 moved in a different direction. Russia designed the AL-41F1 to serve many combat environments at once. High-altitude interception with low-altitude maneuvering, quick bursts of thrust and compatibility with existing manufacturing lines. It is an evolution of the AL-31 family used on the SU-27. That meant the Felon's engine had to balance thrust and maintenance simplicity with affordability. Even its future second-stage engine, the Asdelier 30, still follows this flexible philosophy. This split in vision sets up the entire comparison. One system aims to be invisible while the other aims to be powerful and versatile. The F-119 is a low bypass turbofan with a bypass ratio 0.3. That ratio might seem tiny, but it is intentional. Lower bypass means hotter exhaust and higher thrust per unit of air. Yet in the F-119 it also reduces the exhaust diameter and helps radar and infrared control. It has a 3-stage integrally bladed fan along with advanced cooling for the turbine blades. All of these parts work together to create smooth pressure transitions at high altitude and during supercruise. The AL-41F1 is also a low bypass turbofan, but its ratio sits closer to 0.6. That detail alone tells the story. A higher bypass flow increases mass airflow and allows high thrust without relying on turbine temperature. It also gives better fuel economy at subsonic speeds. The engine uses a 4-stage fan, 9-stage compressor, and feeds a large afterburner section derived from earlier flanker designs. Inside the F-119, the fan blades are designed for quiet efficiency. Variable inlet guide vanes regulate airflow before it reaches the compressor. This stabilizes pressure during supercruise where airflow is still supersonic around the inlet. The compressor itself maintains high pressure ratios without sudden surges. Every stage reduces radar reflections and controls temperature distribution. The AL-41F1 fan is shaped for high mass flow. Russia prioritized volume of air instead of cross-sectional stealth. Its compressor stages are durable and simple to manufacture, and they are optimized for rapid acceleration and deceleration. This is why the SU-57 can go from military thrust to afterburner so quickly. Its responsiveness is essential for its close-range maneuvering philosophy. Before we move forward, here's a question for you. If the AL-41F1 accelerates faster, does it also lose efficiency at high supersonic speeds? Hold that thought. We'll return to it once we reach thermal loads. The F-119's combustor uses advanced cooling channels and precise fuel spray patterns to maintain uniform temperature. The hotter a turbine runs, the more power it produces. But the Raptor cannot afford uneven heat because it exposes structural weaknesses and increases infrared signature. Engineers therefore found a balance where the engine stays hot enough for performance yet cool enough for stealth. Meanwhile, the AL-41F1 combustor focuses on high energy output. Its temperature management accepts wider thermal variation and prioritizes thrust over tight infrared control, but that gives it more short-term punch. Russian engines traditionally accept higher thermal stress in exchange for high thrust under demanding maneuvers. The AL-41F1's turbine blades use a mix of single crystal and directionally solidified materials. However, there is no publicly available data proving a shorter turbine blade lifespan compared to the F-119. This leads into the next major difference about how each jet handles heat when flying fast. When the F-22 supercruises, the F-119 must maintain a stable temperature distribution for several minutes at a time. The engine uses complex internal cooling, including air bled from the compressor and fuel-based heat exchangers. That cooling keeps turbine blades intact and prevents thermal spikes that could show up on infrared sensors. The AL-41F1's higher bypass ratio increases drag inside the inlet, and the legacy design of the compressor limits how long the engine can stay near maximum temperature. While the SU-57 can achieve supersonic flight without afterburner under certain conditions, its ability to sustain supercruise for long periods is not well documented and is generally considered more demanding than in the F-22. So, if thermal stress limits sustained performance, why does the SU-57 still rely on the AL-41F1? That answer becomes clearer once we discuss thrust vectoring and agility. But before we move forward to that, what's fascinated you most about these two engines? Drop your thoughts in the comments below. So both fighters use thrust vectoring, but their goals are not the same. The F-119's nozzle can deflect up to 20 degrees vertically. It is a two-dimensional nozzle designed to keep radar reflections predictable. The rectangular exit also helps manage the shape of the exhaust plume and lower infrared output. Vectoring in the F-22 supports controlled post-stall maneuvers, but only within ranges that maintain stealth geometry. The AL-41F1 uses round nozzles with full multi-axis deflection, typically within 15 degrees on each engine. They can deflect independently, allowing the SU-57 to rotate in dramatic ways. These nozzles are easier to manufacture and give the Felon extreme agility at low speeds. But this choice also reveals a compromise. Round nozzles increase radar cross-section and infrared exposure. Russia accepted these penalties because they wanted maneuverability for dogfighting and missile evasion. The F-22's inlets are built for stability at high speeds. They use serpentine ducts to hide the compressor face from radar. The geometry slows and stabilizes incoming air. If the airflow becomes turbulent, the engine could surge during supercruise. This is why the Raptor's intakes are fixed and carefully shaped. The SU-57 uses variable geometry inlet ramps. These ramps manage airflow during high angles of attack, ensuring the AL-41F1 receives enough air during sudden maneuvers. They are less optimized for radar reduction but excellent for airflow flexibility. These inlet differences explain why the Felon can perform extreme maneuvers without starving the engine, while the Raptor can maintain stable supersonic speed for extended periods. Inside the F-22, fuel acts as a thermal sponge. Before reaching the combustor, fuel circulates through heat exchangers connected to avionics and hydraulic systems. This keeps internal temperatures low and reduces thermal spikes near the nozzle. The F-119 depends on this system to maintain stealth and reliability. The SU-57's fuel system follows typical Russian design, with multiple tanks spread through the fuselage and wings. Its setup focuses on delivering fuel quickly to the afterburner and keeping flow stable during high-angle maneuvers. Unlike the F-22, open sources don't show the SU-57 using fuel as a major thermal sink. And the AL-41F1's cooling system, at least in public documentation, places far less emphasis on stealth-oriented temperature control. The F-119 exhaust is flattened and shielded by the Raptor's tail surfaces. Cold bypass air mixes with hot core exhaust inside the nozzle to reduce temperature before it exits. That mixing, combined with the nozzle shape, significantly lowers infrared visibility. The AL-41F1 has circular nozzles that expose the entire exhaust plume. It produces more heat, especially during maneuvering. The SU-57 incorporates infrared-reducing coatings and airframe shaping, but it cannot match the thermal discipline of the F-22's propulsion system. The F-119 was designed for long service intervals. Its high-temperature alloys, cooling passages, and digital monitoring keep wear under control. Public sources note significantly extended time on wing compared to earlier fighter engines, although exact overhaul intervals are not released. The AL-41F1s often require more frequent inspection and overhaul due to higher thermal stress and simpler cooling. Estimates vary, but typical time between overhauls is significantly lower than the F-119. In practice, the F-22 benefits from stable thrust at every altitude. Its engine allows predictable maneuvering, long supersonic transit, and low visibility. It is not built for dramatic airshow maneuvers. Instead, it delivers controlled performance. The SU-57 benefits from rapid throttle response and high agility in close combat. Its engine can handle abrupt changes in angle of attack and sudden bursts of thrust. This supports the Felon's multi-role mission set. These behaviors come directly from the design philosophies introduced at the start. Two fighters and two completely different visions of air combat. The Raptor hides behind precision and control, while the Felon embraces agility and flexibility. So, which exhaust design do you think gives the bigger tactical edge today? Share your take in the comments. And if you want more engineering deep dives like this one, like the video, subscribe to the channel and share it with someone who loves aviation.